Alright, Chapter 8, Section 2, Properties of Exponential Functions. In this lesson, we're going to learn to identify the role of the constant in y equals ab to the cx. We're going to use e as a base. And we're going to talk about continuously compounded interest. Alright, so far we have graphed functions in the form of y equals ab to the x power for a values greater than 0. Alright. When a is negative or less than 0, the graph is a reflection of the positive one over the x-axis. So let's just kind of look at the diagram here and let's kind of inspect it. So what we did here in the book was we have an x value and we have y value when a is positive and a y value when the exact same a is negative. So we're able to plot our points. The red one represents when a is positive. The blue one represents when a is negative, and what do you notice? They both have an asymptote of y equals 0, and they both mirror each other over the x-axis. Okay, pretty good, interesting stuff there. So let's just jump into it. Let's just graph y equals -4 to the 2x power. So we're going to drop a handy-dandy graph down. We're just going to put one right by here. Let's set up some charts. Let's do some stuff real quick. Make it easy for us. Okay, so let's set an XY graph, or I should say table. Okay, so let's do -3, -2, -1, 0, 1, 2, and 3. So y is going to be -4 times 2 to the -3, -4 times 2 to the -2, -4 times 2 to the -1, -4 times 2 to the 0. You guys, I'm just being repetitious here. Okay, -4 2 cubed. Okay, 2 to the cubed, or 2 to the -3 power is really 1/8. So this is really going to be -4/8, which is really -1/2. So when x is -3, 1, 2, 3, y is -1/2. Okay, so when x is -2, y is really -4/4, which would be -1. Okay, so when x is -1, it's really -4/2, which would be -2. Alright, when x is 0, y is -4. Alright, when x is 1, y is -8. When x is 2, so 2 times 2 is 4. 4 times -4 is -16. So you see we got exponential decay right here. It goes down. Easy enough to graph, right? Just plot your points. Just solve for your, or plug in for x, solve for your y, and plot your points. Not that hard. Alright? You can graph an exponential function as it translates to the parent function. Okay, you guys have seen this. Write it down. Y equals ab to the x minus h plus k. What do you think the h and k values do? The exact same thing they've done for parabolas and everything. The k value is going to translate us left or right, and the k value is going to translate us up and down. So h is left and right, k is up and down. So we're really just going to look at the graph in the book. So you have the parent function of y equals a times 1/2 to the x, so that's exponential decay. So we're going to, that one's the one drawn in red. Okay, but now it has +2 and +3, so we know that's going to translate us 2 units to the left and 3 units up. So from the parent function, all we have to do is translate 2 units to the left at every point and 3 units up. And the blue one represents our translated graph. Okay, remember our horizontal asymptote was y equals 0. Well, with this +3 right here, our horizontal asymptote has changed. It's now going to be y equals 3. Okay. Easy enough. So graph y equals 9 times 3 to the x plus 3 minus 4 as a translation. So let's go ahead and plot a graph. It's going to get exponentially higher pretty quick. So what does that plus 3 and minus 4 tell us? Well, that plus 3 tells us we're going to go left 3, and then minus 4 tells us we're going to go down 4. Okay, so the parent function is y equals 9 times 3 to the x. So let's plug some values in for x. Negative 2, negative 1, 0, 1, and 2. So when x is negative 2, it's really 1 over 9, so it would be 9 over 9, which would be 1. When x is negative 1, it'd really be 9 over 3, so it'd be 3. When x is 0, it'd be 9. When x is 1, it'd be 27. When x is 2, it'd be 81. So let's graph that real quick. So when x is negative 2, y is 1. When x is negative 1, y is 3. When x is 0, y is 9, 4, 5, 6, 7, 8, 9. When x is 1, it's 27. So it's like something like this, and it's going to go up pretty quick. So there you go. That's the parent function. Now we got to translate it. 3 units to the left and 4 units down. So 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. 1, 2, 3, 1, 2, 3, 4. That should be enough points. And there's our translation, left 3 and down 4. Okay, pretty easy stuff thus far. So now let's talk about probably the neatest thing about this, the real world functions. The half-life of radioactive substance is the time it takes for half the material to decay. The hospital prepares 100 milligram of technetium-99m, which has a half-life of only 6 hours. Make a table showing the amount of technetium used after each 6-hour intervals for 36 hours. Then write an exponential function, okay, for after 75 hours. So understand this. It is reduced by half each 6 hours. So here's what we got. We got the total number of 6-hour intervals, the total number of hours elapsed, and then how much technetium we have. So when we start, we had 100 milligrams. So after the first round of 6 hours, we have half. So that's the first round. After the next 6 hours, we have 25. After the next 6 hours, 12 and a half. After the next 6 hours, 6.25, so on and so forth. So the decay factor of a half-life is exactly 1/2. But that half cycle happens every 6 hours. So we're going to use whatever the cycle of the half-life is as our denominator. So we know how many cycles or how many half-lives we go through. So x is going to be the number of hours elapsed. So x over 6 is the number of half-lives that happen. So our equation in this case would be y equals 100. 100 was our starting sample size, times 1/2, that's our decay factor, times x over 6, where x represents the hours we're evaluating, and 6 represents how often the half-life happens. And you just plug it in your calculator. So next example, arsenic-74 is used to locate brain tumors. It has a half-life of 17.5. Write an exponential decay function for a 90 milligram sample and find out how much is left after 6 days. So y equals ab to the x power. Y equals, well, our sample size was 90. Our decay factor is 1/2. We're evaluating it after 6 days, but the half-life is 17.5. So there we have it set up right. And now we're just going to evaluate. So we're going to type in 90 times 0.5 raised to the 6 divided by 17.5. So we're going to get about 71 milligrams. So we have about 71 milligrams. So This one looks like ours. The reason, if you look at it, it's 2 over 35 is they got rid of the fraction. Okay, they got rid of the fraction. Okay, the next part of this, properties of exponential functions. Okay, at the right, there's a part of a graph of a function where y equals 1 plus 1 over x to the x power. Well, that graph's asymptote is y equals e, where e is an irrational number approximately equal to 2.71828. Okay, in a later lesson, we'll explain why this is very useful for growth and decay and how we can use it. Okay, so on your calculator, let's get our handy dandy calculator out and see if we can't find this thing for us. Let's find the E button. Okay, find the natural log button and use your E buttons a second from that. So let's just evaluate what it says. Find the E of 2. So hit your second button, natural log, and then you just type in your 2. 7.38. Pretty easy work there. We're not worried about graphing it right now with the calculator. We'll graph it by hand. So in previous courses, we probably studied simple interest and compound interest. Well, the more frequently the interest is compounded, the more quickly the amount in the account increases. So what we have here is when you see the word continuously, we have a formula for continuously compounded interest. So it's going to be A equals PERT. The amount in the account equals the principal times the E raised to the rate in times. So A equals PERT. So let's see if we can evaluate that for a second. Suppose you have $1,050 at an annual interest rate of 5.5 compounded continuously. How much will you have after 5 years? So A equals PERT, because it's a continuous. The amount we're going to have is going to be equal to the principal. Well, how much did we start with? $1,050 times E. Well, what was my interest rate? 0.055. Remember, we put it in decimal form. And how much time? 5 years. Easy job for our handy dandy calculator. So let's hit the clear button. So it's 1050 times E raised to the 0.055 times 5. So we're going to have 1382.36. 1382.36. So that's how much we have in our account. Always round to the nearest penny unless the book says otherwise. So, next example. Suppose you invest $1,300 at an annual interest rate of 4.3% compounded continuously after 3 years. So that'd be 1,300 times E times 0.043. Remember, how do you get your decimal from percentage? You just divide it by 100. My time was 3 years. So again, this is just easy calculator work for us. So it's going to be 1,300 times E times 0.043 times 0.043. That's a big difference now. 0.043 times 3. $1,479. So we're going to have $1,479. Hopefully that made sense to you. That's pretty much the lesson.